All right, for our next talk, I'd like to introduce Barbara Dietiker. Unfortunately, Barbara couldn't make it here today with us, so she provided a recording of her presentation. So take it away, Barbara.
Sorry, Kayla, it's just freezing up on me momentarily. Oh. There we go. I think I'm through now.
Okay, thanks, Tim.
I apologize, Kayla. The video is just locking up on me, so let me just open up the other file here. I'll just be one moment getting that ready.
Okay, no problem. Not a problem at all, Tim. Thanks. I guess I did forget to mention that we are moving into our next technical session on geological characterizations. So we'll be finishing off the day in this realm, and Barbara's going to kick it off for us. And it looks like we've got the video up on screen here. There we go.
My name is Barbara Dietiker, and I'm going to present insights into buried valley imaging using two different seismic surveys in Geulph and Elora, southern Ontario. Buried valleys are important aquifers, which is why the goal of the study was to image the valley geometries and fill characteristics. Additionally, the HVSR method was tested to provide reconnaissance information on the presence of buried valleys, where a number of dense till units are present. After showing you the locations, I will compare borehole, microtremor horizontal to vertical spectral ratio, and seismic reflection profiles in terms of information details and cost. I will display results from 3 seismic reflection profiles, focusing on the interpretation on the valley walls and the fill. The last part showcases HVSR, how it might help interpreting seismic reflections, and what information can be gained about valley location, shape, and orientation from a profile of stations. In southern Ontario, here you see the surficial geology map. We acquired 2 transects in Elora and 1 in the Geulph Arboretum. The 2 transects in Elora are almost 700 and 900 meters long, with 43 and 28 HVSR stations along these sections. The Arboretum profile is roughly 500 meters long, with 23 HVSR stations. Core-logged boreholes are expensive but provide detailed information about lithology and lithostratigraphy. They do not provide lateral information. Additional boreholes might provide limited insight. Lateral connections are still guesswork. Horizontal to vertical spectral ratio method fills this gap by linking spectral peaks to borehole lithology and providing more lateral insight, augmenting already known information. Of course, a seismic reflection profile adds even more detail, like different horizons, but it is more costly. With a profile of HVSR stations, lateral information is augmented at a decent expenditure. Let's get a quick overview of the 3 shear wave seismic profiles with a focus on valley walls. At Elora 1, a buried valley with steep walls was interpreted, confirmed by 4 boreholes. At Elora 2, similarly, we have info from 4 boreholes, and the buried valley was imaged with steep walls. There are no reflections indicating the valley edges because the side walls are inclined more than 45 degrees. Arbo 2 images a buried valley in a different setting where the valley walls are less steep and the southern edge has a 2-step incline. Let's look at the valley fill in more detail. The fill at Arbo 2 is characterized by medium amplitudes and chaotic reflections. At Elora 1, we find high amplitude reflections near the valley edges and a transparent center. Borehole information details the origin of the strong reflections as the base of diamecton and some sand units. At Elora 2, there are strong reflections near the edges and a more transparent center, and a package of high amplitude reflections at the northern edge. These reflections have similar wavelengths, which is why we think that these are reverberations or ringing caused by a very high impedance contrast at the top and the bottom. The borehole near the southern edge has sand filling the valley and creating a strong reflection similar to Elora 1. The strongest reflection stems from the top of sand. Since the reflection is weaker in the center compared to the edges, we think that the center fill is different. Now let's focus on the HVSR method and how it can aid in subsurface reconnaissance. First, we assess how many stations are needed to survey a structure. 2 are definitely not enough. With 3, we get a first hint. We now have stations at a 100-meter distance. With a 50-meter station interval, we can come up with a decent estimate where resonance maxima or peak amplitudes relate to stiff materials or bedrock, in this example of Arbo 2. With denser stations, about 20-meter intervals, and adding at the sides, the buried valley can be well defined. Once again, Arbo 2 is used as an example to demonstrate how HVSR aids in reflection interpretation. Usually, strong reflections mark the bedrock surface, but it is sometimes not easily recognized. When HVSR is added and the resonance maxima are linked, it can be used as bedrock depth estimates. And it is easier then to identify the bedrock reflections. For Elora 1, we compare the bedrock surface from HVSR resonance to the seismic reflections. Of course, there are differences, and especially in the very near surface, there are many resonance peaks. Comparing with seismic sections, there are reflections that were not interpreted. These can be linked to a diamecton layer with the help of the borehole. Let's look at how valley location and shape can be estimated from HVSR. At Elora 2, bedrock is estimated from the deepest resonance peaks, linked by the black line. However, we note that the amplitude maxima are at very shallow depths in the center of the profile, and many local peaks exist within the valley field. These are marked by blue X's. Comparing with reflection interpretation, the highest resonances match a near-surface till layer, and the intra-valley peaks were interpreted from reflections as the bedrock surface. The reflections themselves highlight the ringing package, where bedrock interpretations differ most. Maybe the valley is broader than seismically interpreted, and the HVSR estimation is correct. Further investigation is needed. Now let's look into azimuthal HVSR analysis. During the regular processing of HVSR, the combined horizontal to vertical ratio is calculated, resulting in H/V amplitudes as a function of frequency. The fundamental frequency is found at the amplitude maximum. There are also local maxima. For enhanced processing, H/V amplitudes are calculated for azimuths from 0 to 180 degrees in intervals of 5 degrees and displayed as a function of frequency and azimuth. The azimuth of the highest H/V can be found here, displayed as white dots. Thus, we find azimuth at the global maximum, here 45 degrees, shown as rose color. and at the local maxima, here 30 degrees, shown in brown, and blue for 120 degrees. The azimuth is an indication of the strike of a subsurface structure. Here for Elora 1, all relevant azimuths are displayed in color. Azimuths related to the valley floor show as pinkish brown colors, which refer to a roughly east-northeast strike, which could also be displayed like this. At Elora 2, the deepest valley floor has also an east-northeast strike, which matches the valley orientation. However, there is the northern side of the valley, which has a southeast strike, and a northern side which has a north-northeast strike. Comparing with seismic reflections and the interpreted horizons, this area matches the zone where a deeper valley is suspected. Earlier, we already pointed out this zone, meriting further investigation. I hope I was able to demonstrate that HVSR surveys provide valuable lateral information at moderate expense. There are many advantages to HVSR profiles compared to gravity, for example, as HVSR might also provide information about subsurface layers and directional trends of structures. Additionally, we demonstrated that HVSR aids reflection interpretation, even though it can never surpass the detailed information gained from reflection seismology. Finally, borehole control is very important, and reflection interpretation would be very difficult without it. In summary, the two seismic methods, reflection seismology and HVSR, provide useful information for any groundwater-related subsurface investigation. Please feel free to send your questions to my email. I'm happy to answer. Thank you for your attention.
Awesome, and thank you, Barbara, for preparing that presentation for us and sharing your work. As Barbara mentioned in her talk, if you have any questions for her, you can reach her directly,